Hello students, in this session we will discuss a problem regarding the voltage divider bias. So look at the problem. For the voltage divider bias, he mentioned type of bias, configuration, determine IC, VE, supply and collector emitter voltage, base voltage and R1. So these are the things. So looking at the diagram also, it is a voltage divider biasing circuit. In this, he already given some points. So by using the voltage divider bias procedure, we will solve this problem. So for that purpose, first modify the given circuit. So modifying the given circuit, we can convert like this. The voltage will be converted into the Thevenin's voltage, and we have a resistor, that is R Thevenin's. We have a resistor, that is the R Thevenin's, and that will be given to a transistor. The transistor, so here this will be take as the load. This should be Thevenin's circuit. This will be converted into a Thevenin's circuit, and this branch will be take it as a load. So for that purpose, so transistor, and it consisting of the voltage, base voltage, that is 10.6 volts, and it has the supply, that is VCC, and the resistor is there, that is 2.7K, and it has a branch. So 10.6, we know that we can take it as the VC. VC means collector voltage, and here we have a terminal voltage. We don't have this voltage, that value is the V, and it is connected to a base. So 1.2 kilo ohms. This is the modified circuit. In this circuit, he doesn't give an R1 value, but he given R2 value. Take this is the R2. Okay. So from this we can write how we can find out the Thevenin's voltage. So Thevenin's voltage I can write like this. Thevenin's voltage is nothing but this VCC by VCC into R2 by R1 plus R2. So by looking at the theory of the voltage divider bias, you will understand this concept. And how can we find out this R Thevenin's value? R Thevenin's value equal to R1 into R2 by R1 plus R2. By using these two formulas, we can find out V Thevenin's and R Thevenin's. So, okay. Next, we will discuss each and every point. The first question is, he is asking to find out the collector current. What is collector current? Collector current, I can directly write beta into base current. So in beta is already given 100. So what is the current entering into the base? Is 20 microamperes. So I can write this is the 20 milliamperes. Therefore collector current is 20 milliamperes. 20 milliamperes. Next, just find out C. We can find out the VCC. So what is VCC? This voltage. VCC is this voltage. He need to find out. What is the formula for VCC? Looking at this branch, we can write VCC formula here. So I can write for VCC minus VCC plus 2.7K into IC plus 10.6 is equals to 0. From this I can write, from this I will find out the VCC equal to 2.7K. What is the IC value? IC value is 20 milliamps plus 10.6. By solving this, you will get VCC value is directly 16 volts. Directly 16 volts. Next, we will find out B value. What is B? Looking at where is the B? V is emitter voltage. So we need to find out this voltage. Actually, this is the ground. Don't forget this ground. So how can we find out the emitter voltage? Before emitter voltage, generally emitter voltage is what? Looking at what is this voltage? This voltage is voltage across this branch. Voltage across this branch means I can write emitter voltage equal to emitter current into emitter resistance. So for that purpose, we need to find out first emitter current. What is emitter current? Emitter current formula equal to base current plus collector current. So from this I can write emitter current is approximately equal to the collector current. So by using this I can write the emitter voltage equal to, so both are same. So what is the collector current? 20 milliamps. So 20 milliamps into emitter resistance is 1.2 K. So by solving this we will get emitter voltage, that is 2.42 volts. So this is the emitter voltage. Next, D. What is D? D is VCE. So D is the VCE. How can we find out D? Generally VCE equal to, if you observe VCE means, look at here. Here we have the VC voltage and VE voltage. The drop between these 2 points is nothing but VCE. So we know the VE value. So by using that I can write VE equal to VC minus V. What is VC value? So VC value is 10.6 minus VE value is 2.424. By solving this we will get collector emitter voltage is 8.176 volts. This is the VCE. And we can find out VB also. VBE. Where is the VBE? Look at here. This is the VBE. VBE. This is the drop between VB and VE. VB and VE. So just write VBE. So in order to find out the VB, just you write VBE, that is, I can write VBE is like this, VB minus V. But if you observe VBE is a PN junction diode. PN junction diode means it has a cut-in voltage of 0.7 volts. Just directly you can write the 0.7 volts. So this is 0.7 volts and we need to find out the VB value, and we have emitter voltage, that is 2.424. By solving this we will get VB value is 3.124 volts. This is VE. Okay, and we need to find out F. So we will find out the most important point here is, in the circuit we are converted this complete circuit into this Thevenin's model. So here the Thevenin's voltage will be equal to the approximately base voltage. So by using that I can write like this: Thevenin's voltage is approximately equal to the base voltage. So by using that I can write, generally what is the formula for Thevenin's voltage here? Thevenin's voltage equal to VCC R2 by R1 plus R2. Okay, so by using this, what is V Thevenin's? Is nothing but VB. So that value is 3.124 equal to VCC we already find out 16 volts and the R2 is 6.8K by R1 plus 6.8K. Okay, by solving this we will find out R1 value is 28 kilo ohms. R1 value is the 28 kilo ohms. Okay, so if we given any problem like this model, we can solve by using the Thevenin's theorem. Okay. First, looking at the diagram, when you are looking at the given problem, it's look like a difficult one. But when you are solving the problem, it is very easy. So by using this procedure, it is very easy. Okay. Don't think big about this transistor. The problems are very simple. He already given everything in the circuit, just we do small calculation, we will get the solution. Okay, the next topic is thermal runaway. So here name itself it is a thermal runaway. Thermal runaway means, thermal means generally heat, runaway means not in control, so what happened, why this phenomena is happen? So in order to understand this, just take a BJT for CE configuration BJT, right? So in this, generally I can write the output current CE configuration collector current equal to beta into IB plus 1 plus beta into ICBO. Here IC, you know that collector current and beta, you know that IB is the base current, that is input current. ICBO is the minority charge carriers current, current flow through the minority charge carriers. So minority charge carriers will affect on the collector current. So that is we have to discuss. Generally, first concept, if temperature of a given BJT increases, then what happen? Concentration of minority charge carriers also increases. So whenever temperature increases, concentration also increases. By that, whenever the concentration of minority charge carriers increases, automatically current flow through the minority charge carriers also increases. Okay, then whenever it is increases, automatically collector current will be increases. So finally what happened? By doing this, when temperature increases, automatically collector current also increases. Okay, collector current also increases. So for what? Practically for 10 degrees Celsius of the increase in temperature will give double the ICBO, minority charge carriers current will be double. So if 10 degree temperature increases, automatically double of the ICBO. Due to this, what happened? Flow of collector current also increases. That will what happen when the collector current flows means what happen? Generally, heat will be produces. When a collector current flows, generally heat will be produces. Automatically temperature also increases. It is a general thing. When collector current is flowing, automatically heat will be produces. Due to that, temperature will be increases. Look at here, temperature increases, collector current will be increased. When the collector current will flow, then automatically temperature will be increases. So both are interlinked with the each and everything. So what happened? So I can write like this. That is, when temperature increases, what happen? ICVO, minority charge carriers current will be increases. Due to that, what happen? Whenever it is increases, automatically collector current will be increases. Whenever the collector current increases, temperature will be increases. So this will be continuous process. Whenever this process is continuous, means temperature increases means what happen? The transistor will become damaged. That means the self destruction is possible. Self destruction of unstabilization is known as thermal runaway, is called as the thermal runaway. So this is the process of thermal runaway. I think all of you understand. But in order to control the thermal runaway, we have some problems. Okay, and we can decrease this thermal runaway. Otherwise, any transistor cannot work in the universe. So we can follow some remedies for this. For that, we can write mitigation of thermal runaway. That means how to remove this. Mitigation of thermal runaway means how we can solve this, the given problem we have to discuss here. The first is, we can use the negative feedback. Whenever if you are using the negative feedback, then automatically we can decrease the thermal runaway. So what happened for that? Whenever collector current increases, that time we have to decrease the base current. Whenever the base current is, we have to decrease the base current. Whenever the base current is decreases, automatically collector current also decreases. So we can control by this method. So how we can decrease this base current? By introducing the emitter resistance. By introducing emitter resistance, we can control this thermal runaway. Next, we can provide the heat sinks. What is the application of heat sinks? Heat sink which absorbs the heat from the BJT and it will reveal into the atmosphere. That is also, it can control the heat. By using these two, we can control the thermal runaway. Okay, I hope all of you understand this session. So this is the problem regarding the voltage divider bias and the concept of thermal runaway. Okay, thank you.